Hi, welcome to the second Tux Sanders Series Invited Lecture of 2018. So today, it's my great pleasure to introduce today's distinguished speaker, Professor Mary Lou Maher from the University of North Carolina, Charlotte. So Mary Lou is chair of the Department of Software and Information Systems in the College of Computing and Informatics at UNC Charlotte, which also includes teaching and research in human-centered design, among other areas. In her time at UNC Charlotte, Mary Lou has expanded the HCI program to include an undergraduate and graduate concentration in the CS and MSIT degrees, and has also established a graduate certificate in HCI, so she's really growing HCI there. Mary Lou is also the director of the Center for Education Innovation, which focuses on innovation in CS education and is home to something like 20 or more externally funded research projects, as well as she's also a professor in the HCI lab. So her research interests span kind of broadly across design and computing, and her academic career has taken a path from engineering through architecture and design computing as well to computer science and information studies. So she's ranged across a broad range of disciplines. Her interests include the cognitive effects of embodied interaction modalities, computational and cognitive models of creativity and curiosity, and design patterns for active learning strategies in CS education. Her research draws on and contributes to human-computer interaction, intelligent systems, CSCW, computer-supported collaborative work, design science, and computational creativity. So she's had a tremendously successful academic career so far, and I don't have time to cover it in any detail at all, but just to mention a few highlights. So she completed her undergraduate studies at Columbia University, followed by MS and PhD degrees at Carnegie Mellon University. And then before landing at UNC Charlotte, she was also a professor of design computing and co-director of the Key Center of Design Computing and Cognition at the University of Sydney in Australia. And when she was there, she also developed and implemented an innovative bachelor degree in design computing. She also spent some time at the US National Science Foundation, where she was the program director in the Human-Centered Computing Cluster and co-chaired the Cyber-Enabled Discovery and Innovation Program, and also started a fabulous funding program that I was very familiar with called Creative IT, and I know from personal experience because I had a grant through that program. And it was a wonderful program which brought together research across areas such as HCI, creativity and cognition, and design thinking. Some of the highlights of Mary Lou's recent research include developing models of motivation, innovation, and diversity in collective intelligence, designing tangible and immersive interaction environments, and evaluating their impact on creativity and cognition, and then the design and study of virtual worlds for collaboration and education. She's the author and editor of 10 books and over 180 publications, and her most recent book, which was published just last year in 2017, is Designing for Gesture and Tangible Interaction. So with that said, I'd like to hand the mic over to Mary Lou to tell us about designing for gesture and tangible interaction. So please join me in welcoming to the stage Professor Mary Lou Maher.
Thank you, Ali. So it's a pleasure to be here. It's going to be really interesting to see how this talk unfolds. I did bring a copy of the book, and I wanted to give you a little history on the book because I decided to make the presentation explain what we were thinking when we wanted to write this book. So I was approached by Jack Carroll, who's the series editor for these series of books by Morgan and Claypool, to write a book that would be sort of available to the people who don't do research in the field, but be available to those who do as well by providing a collection of references that would help them get started or help them advance wherever they were in that field. And so I was thinking, what do I talk about when I was invited by Ali to come and give this talk, because I have a lot of topics that I've touched. And I decided to do, it's sort of a retrospective over about 15 years of work that I've done. And I've selected a few projects to give it some specificity. But the real idea here is to think about designing for gesture intangible, not designing the technology per se, although that's part of it, but designing for the human part of it. Because if you think about it, when you build a system where we interact through gesture, we're effectively designing the gestures that people will use. You can't just do anything. You have to do what the person who implemented the system could sense. And so that has a large impact on what we even think of trying, and it has an impact on what we think. So this will be more about the people side of it. It'll be more about the cognitive effect and cognitive impact rather than the latest developments in what the technology is. I will touch on the technology, but only in service of how it affects the way people think and how it affects how people interact with digital information. So just to be clear, I'm sure most people in the room know what these two words mean, or actually these three phrases, but we're looking at embodied interaction, and that is when you interact with the computer or any kind of digital artifact by moving your body around and by using movements that are usually associated with the physical world rather than the keyboard and mouse or even the touch screen that's become associated with digital artifacts. And we're looking just at two of them. One is called tangible interaction, and that is very specifically in my work referring to when you provide graspable physical objects and you manipulate them and you arrange them to change digital content and to interact with digital objects. And the second is gesture-based interaction, and that is when you have a system that detects human movement, large body movement, or just hand movement, and that enables interaction, again, with digital content and objects. And very specifically, when we did gesture interaction, no touching and no grasping, so we kept them separate. And you'll see a theme through the presentation and the specific projects that I highlight on some of the cognitive issues that are associated with these two kinds of interaction. And so we'll start with embodiment, because that's actually part of the phrase, embodied interaction. And there the challenge is for designers to design gesture interaction is that you really need to understand and you rely on pre-existing mental models depending on our own physical experience. So it's our physical experience that makes us understand how our body movement is interpreted, and that comes with us as we walk up to or use a system that allows us to use that body movement to interact with digital content. Now, the nice thing about that, so that's the challenge, but the nice thing about that is numerous studies have shown that the way we move our hands, so you can see I'm gesturing up here, and there's nothing sensing my gestures. In fact, you're not even understanding my gestures, so why do I gesture? And the reason humans gesture is because it aids thinking. They've done studies in psychology that if you don't let someone gesture, they often experience something called verbal or cognitive disfluency. So they'll get a little confused, things will slow down a little bit. You let them move their hands, and you get rid of the disfluency. That's interesting, because if you think about what we've done with computers and our phones, is we've glued our hands to the device and we don't let them move too much, especially a keyboard. Don't let the fingers move too much. Does that cause cognitive disfluency? Is there another way to think about how we interact with digital content so that we get rid of that effect? And then affordance. How many people have heard the word affordance in this room? Affordance is possibly the most misunderstood word in HCI research and development. But basically, in my understanding, an affordance is how the thing itself communicates to you what you can do with it. So it provides the visual signifiers for what actions you can perform and what things you can do. Okay. Well, now if we're doing graspable and tangible interaction, the affordances that we think of should be sensed by the object. So if we think of waving as being something we might do to interact with a device, and waving isn't sensed, then we've lost that opportunity for that affordance. And so you have to think in terms of what are those affordances. And the benefit is if you actually have a very well-defined interactive system, then it's clear. People will know how to use it just by looking at it. That's the ideal. Okay, metaphor. Metaphor is a very common thing to be used in HCI. The desktop metaphor transformed us. Windows transformed us. Those are metaphors. They provide standardization, and they provide facilities for people to learn how to use them without studying. So before there were Windows and before there were trash cans and all those metaphors for the graphical user interface, you had to go take a course in computer science and learn how to type the commands in. So metaphor enables it for everyday people. And then finally, epistemic action. A lot of the research that I've done on the effect of tangible interaction is that it encourages what's called epistemic actions, which is exploring the task space or the solution space by moving things around and offloading cognition onto the thing in front of you. And so if that's what you want to do, if you want to encourage people to explore, then you want to encourage epistemic actions. You'll see these themes come up over and over. And what I want to do with the presentation is when I go into each of the projects, I'll explain how did we handle embodiment, affordance, metaphor, and epistemic action in the methods that we use to do the design or in the methods that we use to do the evaluation. So it's sort of a compendium of how do you do this, rather than here's some brand new technology. So just an overview. For each of gesture and tangible interaction, I'll look at why is it interesting? Why do we want to do this? What does it give us that we don't have already? What are the design issues? And then for each of the projects, I'll talk about something like context of use. So what you design actually depends significantly on what you're doing. Unlike the keyboard and mouse, which is universal, no matter what application you use on this laptop, a keyboard's going to work for you. That's not the case with the tangible and the gesture interaction. How you design the interaction depends largely on what it's being used for. And then I'll finish up with the design challenges for embodied interaction, which has to do with, as designers, where are the hard parts? And then I'll talk about the research challenges, which means where do we need to do more research in order to get to the point where they become design challenges. So I'll start with designing for tangible interaction. In the first instance, I'll be using the Siftio cubes as our example in the project that we did. And I'll move into how we designed our own tangible objects, but I'll start with the Siftios. So what is tangible interaction? As I said before, it's when you have physical objects. They have a very strong digital correlation to digital objects, and they provide an alternative to using the keyboard and the mouse. And the two projects that we worked on over several years was this idea of the tangible keyboard, where we used the metaphor of the keyboard to decide what would happen if you could actually change what you saw on the keys and you could rearrange them. And so right now we have a keyboard with fixed symbols on each key, and you don't move them. You move your fingers around them. And the second example is what I call tangible models, and that's where the blocks were the basis for augmented reality. So you can't see it here, but each block, the 3D model sort of jumps out of the block digitally with either see-through glasses or on a display. And so now the blocks are actually objects, 3D objects, and that was used in an architecture context. So why is tangible interaction interesting? These are based on the Fitzmaurice paper way back in '96. This has been around for a really long time. But these are not only still true, but they're even more important to acknowledge now that we've had these things around for 20 years. They're space multiplexed. So a mouse is multiplexed according to function. It can change its purpose depending on what you're doing with it. And the difference with tangible interaction is each object has its location in space is what's relevant, not its function. Its function will stay pretty constant in most implementations, but it's space multiplex. That's a completely different way of thinking about it, because everybody says, well, isn't the mouse Tangible, well, the mouse is graspable, but it's time multiplexed. Concurrency, one of the things that's really awesome about tangible interaction is that you put these things out on a tabletop or whatever your interactive device is, and they can be used at the same time. So the mouse can only be used once by one person, and now you have things that can be used at the same time. So you're taking two objects and you're putting them together, or you're shaking them, or you're stacking them, so they have concurrency. The third one, strong specific devices. That means that you can actually make a single object have a very strong connection with some kind of digital content. It's not generalized. It doesn't have to be generalized. That's really powerful when you're thinking about solving an interaction problem with something complex like genes, or something complex like complex information or data. It can be very strongly attached. It's spatially aware. It should be sensed where it is in space, and that should matter. And it's spatially reconfigurable, so you can manipulate it and move it around. So what are the design issues? When you're designing this kind of technology, you have to think about the interplay of the virtual and the physical. What's the mapping? What do these devices do? We saw a demo this morning where they had a combination of touch and tangible, where there are these little hockey puck looking things that you put on the table. How do you decide what you do with that and what you do by touching? And so that interplay becomes part of the design process. And what you want to think about as a designer is what's meaningful from the user's perspective. Because if it's arbitrary, not only are you going to cause that cognitive disfluency, but you're going to make it very difficult for people to learn how to use the system. Another issue, this selecting from multiple gestures and actions. If you think about it, we have standards everywhere that enables things to happen well beyond the individual. American Sign Language, before that it was really hard for deaf people to talk to each other. You had to standardize it. The way we use our phones, what we do with touch, what we do with touch and drag, what we do with swipe, that's been standardized. Through that standardization, we've been able to develop apps that people can figure out without a user manual. They can play around with it. They remember what they saw before. We don't have anything like that for tangible. We don't have any standards. Every tangible device that's used as an interactive device, they set their own standard. Even with something like Siftio cubes, how shake is interpreted is different for every application. Does it make sense in the same way? Usually not. And so the real challenge is we don't have any standards. And from my perspective, until we get these standards and do it thoughtfully, we're going to end up, first of all, with systems that are not very learnable, but we might end up with the QWERTY keyboard. Now, if you think back, how did the QWERTY keyboard get to be? Why are the symbols in that order? Well, they're in that order so that when the mechanical device that shot the arm down to put the letter on paper through the ink ribbon, it was so that when you were typing, it decreased the chance that two keys would be coming from the same direction and sort of interfere with each other. That's how it was determined. But that has nothing to do with our cognitive impact of having it in that we've learned it. They've produced numerous keyboards since that, like the Dvorak keyboard, which is cognitively more attuned to human use. But they can't change it. The standard's out there. No one's ever going to change. With no standards for tangible user interfaces, we have the problem that a standard will emerge because it becomes popular or it serves some other purpose, but it's going to not be suited for human use. Cross-disciplinary, it's really hard to be a designer in this field. You really need to know computer science, you need to know about design, you need to know about cognitive sciences, you need to know about engineering. And so the people who design these things don't always have that kind of collection of people around, and so they get skewed towards whatever they know instead of actually benefiting from the cross-disciplinary part. And again, no standard input and output, there's no consistency. I can show you that. We've done some papers on that that shows all those things that are out there. Everyone's just come up with something else without standardizing it. So what did we do? We came up with this tangible keyboard. We set the design goals from my previous work where we found that tangible interaction had strong associations with creativity and creative cognition. We thought we would design tangible keyboards so that you could change what was on the screen of the siftables to be rearranging things for different creative tasks. And we did it for shapes, words, and sounds. And we ran a bunch of usability studies. And we found, first of all, our intuition about what would you do to shake and what would you do when you neighbor was not necessarily the intuition of our users, so we had to back off on that and redesign that. But we also found that for some creative tasks, that rearranging of the cubes, they felt like it slowed them down, that they could do it faster in their head. And so we were curious, what's faster in your head and what's faster by moving it around and using epistemic actions? I'm going to just show you, just so you get a feel for what it is, I'm going to just show you a short video of the, we called it our DINKS project. They were digital interactive keys. Let's see. Come on, play. That was really loud. Let me just turn that down a bit. Okay, go. Well, now it's... So use the touch screen to put the object on the cube. And that sort of populates the cubes with the symbols instead of being given fixed symbols on the cubes. Once it's on there, there were different mechanisms for changing what you see on the cubes. And then different interpretations of making them touch each other. We thought about some cubes being objects and some cubes being like control objects, so you could change the color by pouring the paint bucket onto the object or shaking it. So you get a sense of what it was. And we actually spent quite a lot of time thinking about what to put on the objects and what would be the interpretation of moving them around. And we did a pretty terrible job because the users found that it wasn't intuitive, they had trouble discovering it, but they came up with quite a lot of ideas on how to make it better. So I'm going to talk a little bit about the methods, how we came up with the idea, and how we did the evaluation, because it's these methods, I think, transfers beyond just DINKS, but how would you do this for some other context of use? And so the metaphor we thought was a pretty important concept, that if you can use a metaphor, then it allows the user to take something familiar as the basis for understanding something they've never used before. And that linguistic concept is really powerful in HCI, as we've seen over and over again. So we had to figure out what transfers. And so from the keyboard, we took the idea of symbols. What is the alphabet, effectively, for that task? So we went from letters to words for the poetry application, to shapes for the shape configuration, and to musical notes for the music. And then the keys, those are the things that you touch in order to make compositions, and instead of touching, we rearrange them. And we did an evaluation. We actually did two kinds of evaluation. We did something called the heuristic evaluation. For those of you who know Nielsen's heuristics, it's a really good way to get the really poor decisions about your design out of the way quickly without doing user studies. And this, we found we came up with a lot of interaction and consistency. And we came up with a lot of system/world mismatch. Even though intuitively it all felt good in the beginning, when we actually analytically looked at our design, it was not very good. And then we did a Wizard of Oz in an interview study, and that was on the application that's called Silly Poems. And that was fascinating because this was someone who writes poetry interacting with our system. And this is when we began to appreciate that maybe it's not good for everything, because she found it very cumbersome to have to move the words around. Because in a poem, it's not really spatial reasoning, it's much more linguistic. And she could keep that in her head much faster and change it much faster than she could by moving things around. And so from that, we've learned, and we've done numerous studies since then where we've compared tangible and non-tangible on spatial reasoning tasks, tangible and non-tangible on non-spatial reasoning tasks. And we've concluded that their real benefit is when the task requires some sort of spatial reasoning that you can offload onto the objects. And so then from out of this, we decided Nielsen's heuristics were pretty good. They were really helpful. And we could redefine them. What did they mean when you're talking about tangible? Because Nielsen's heuristics were developed for screen-based interaction, and this was not screen-based, it was graspable. We also found that there were two heuristics that weren't part of Nielsen's that were really important. It has to be easy to discover. In the interaction that we design on the web, or even the phone now, there's so many standards that the person will eventually get to it. They'll eventually figure out how to do it because they'll do trial and error. Often in tangibles, they won't ever figure it out unless you tell them, unless it's designed to be easy to discover. And then minimize physical strain. Obviously, any kind of embodied interaction, when you design it, you don't want someone to be holding their hand up for 10 minutes because it starts to hurt. The tangible models one, that one's been out there a little bit longer. I'll go through this a little more quickly, but basically the context of use redefined what these strong specific objects were. They weren't flat screens, they were 3D models. The task was to configure a space with these 3D models. We connected it to an ArchiCAD application, not AutoCAD, because AutoCAD wouldn't let us change the input devices at the time. We used tangible blocks with the AR toolkit, so that gave us the ability for the devices to spawn these 3D models. And it supported synchronous collaboration, which was really awesome. We used a tabletop display with a plan view of the building, and then a vertical display that showed the 3D perspective. And what was our method here that we thought was the most helpful was a protocol analysis. And this is when you collect data from a think aloud process. So we gave them two conditions: use ArchiCAD for the same task with keyboard and mouse, use ArchiCAD with these new ways of configuring with tangibles, and then compare the two data sets. And we found with the tangible models, there were far more problem-finding behaviors, and there were more unexpected discoveries in their two kinds of actions, perceptual and revisited. We also found that they discovered new visual-spatial features via epistemic actions. So this was a comparison of protocols of several pairs of designers using the two different conditions. And it was really enlightening and was kind of foundational for us that there was a significant difference between the keyboard and the mouse and the tangibles for a configuration task. And as we moved on with our other studies, we had to refine that because it wasn't that simple. You can't take any task and say tangibles are better than the keyboard. So the tangible models, why would you use those and where are the benefits? When you build a tangible model, you have to think about what is the movement of the 3D object, what does it mean? Because people spend a lot of time moving them. And then inspection, and that's when you might click on it or you might look into it. We also found that it wasn't as simple as actions on 3D blocks, which is where we started. We thought that's what it's all about. It's about moving these blocks. But there were a lot of gestures. People were still using their gestures, these big hand movements to explain things, and then they'd go back to the objects. And by making it tangible, it encouraged that, because when you're using the keyboard, you don't take your hands off the keyboard very much. You leave them there. We also found there were a lot of general gestures that had nothing to do with what they were doing, but we thought it aided cognition. And there are a lot of touching. A lot of times people just touch things to think. They don't move them. And that was really interesting. So I guess the most important one is that very bottom one on the benefits. We found that the increase in problem-finding behaviors, the process of re-representation, those are things that are associated with creative design. And so when you can use tangibles, you have the opportunity to increase creative cognition. Okay, so now we're going to look at gesture, and then I'll pull it all together. There are two projects I'll talk about. One is something called gesture commands, and that's when you use your body movements to replace effectively what you could do if you touched or you had a keyboard. So how do you step back and think about how has my body movement become an alternative? Why would you do that? In public displays, you don't want people touching your screens. It's not sanitary. It's possible that the screen is taller than they are, so there's parts of the screen they can't touch. There's all sorts of reasons why there are going to be situations where you don't want touch. But you want the same thing that touch affords. So you want them to be able to select and move things around. The second one is a gesture dialogue, and that was a really fun project. That's where we were looking at how can you interact with a digital artifact only by body movement, and it responded only with body movement, and that was our willful marionette project. So why is this interesting? We see more and more public walk-up and use displays. We see things in museums, all sorts of venues where touch isn't possible. The prices come down and the availability of these remote actuators, sensors, displays, it's now possible that this could be done without costing a lot of money, and so we don't need highly specialized contexts for this. Anyone can do it, anyone can program it. It also creates a sort of a sociable, sort of multiple use interaction. It's a way of getting multiple people to work together, to collaborate together, to engage in some public activity together. And if it was all touch, I don't know if you've seen the difference between a display that's gesture and a display that's touch. If it's touch, someone will go up and touch and everyone else will stand back. But when it's gesture, people are more encouraged to go up and use it. Also, gesture is part of the way we are in the world. And so one of the reasons for looking at this is, why aren't we using gesture when we interact with other kinds of artifacts than humans? Now, what are the key design issues? People don't know they can do something with a display that's gesture-based unless you indicate that or engage them. And how do you engage them? Otherwise, they're going to think it's just like that one over there, which works without me doing anything. It's just running a series of slides. How do you communicate that it's actually something that if I move, it'll change? The clear and consistent visual feedback, it's a real challenge in gesture-based interaction because we don't have clear and consistent gestures. So again, lack of standards, different people think of different ways of interacting. Ergonomic gestures, this is possibly the biggest challenge. Almost every gesture interaction system that's out there causes physical fatigue. And people will play with it for a little while and then they'll walk away because they're exhausted. I don't know how we're going to fix that, but that's a real problem. And why is that? I don't get tired standing up here gesturing. I'm going to be gesturing for about an hour, and I'm not going to feel tired. And it's because I'm not doing repetitive gestures. But when you design a gesture interaction system, you're going to have to use same gesture does same thing, so you're going to have to do the people are going to have to perform that over and over again, and that's where the fatigue comes from. Designing discoverable gestures, we're getting a little bit better at methods that help us with the discoverable part. I'll be talking about the methodology where you can actually ask people to try a bunch of gestures that they think, so you can sort of tease that out. Inaccurate gesture recognition is a design challenge because everybody's body is slightly different. I wave this way, someone else might wave this way, and yet that's a wave. And so how do we do gesture recognition in a way that's consistent. We did the walk up and use information display, and that was to see if we could have discoverable ways of doing it. We couldn't. We actually had to help people along by saying, come on, move closer. So we had little doughboys there that would say, move closer. And then we had to provide a hand on there to show if you put your hand here. So it was really hard for people to discover it. I think the most difficult part of that was that this display was next to one that wasn't gesture-based. And so they just expected that it would just do what it does, and I had nothing to do with changing it. And that's, for us, it was a proximity issue, but if you think about it, it's a mental model issue. People approach these things, these digital artifacts that are in the world, with their mental model of what should be happening next. And if there's a mismatch between their mental model and the way it's supposed to, the way it actually works, it's really hard to bridge that gap. It's been called about the gap of execution. We know how to do it when it's screen-based and it's a keyboard and mouse there, but we don't know how to do it with gesture interaction yet. So we used a few concepts. We used the mirror concept to engage people. They could see a shadow of themselves on the screen, and as they move, their shadow moves. Then they're like, oh, it's sensing me. Like that was an indicator. It's a very common sort of trick to get people to pay attention to displays that are sensing them as individuals. We also did a gesture elicitation study, and we found that the one that people really thought was easy to discover was to use the hand with a kind of pointing motion. Nothing else was easy for them to discover in this context of use, because you usually interact with this kind of information with a mouse and a pointer, and just replace the hand was easy. It caused fatigue. So we came up with some, we did the heuristic study. For each of the heuristics, we redefined what do they mean for gesture. The last time you saw this slide was what do they mean for tangible. And then we came up with some new heuristics that aren't in Nielsen's original 10, provocative interactions. Somehow you have to provoke the person to walk up, and then muscle fatigue. Before I go into the willful marionette project description, I wanted to show you a video. Has anyone seen a video of the willful marionette? This is a fascinating project. This is a project that we did with 2 artists in residence. And their intention was really different to our intention. So their intention, let me get rid of the sound. Okay. Their intention was to take a 3D replica of one of the artists, his name is Bill, print it out and string it up and make people uncomfortable. So they made him blue and they made him naked. And they wanted only to provoke. And we are then in the process, we needed to design the interaction model as the interaction designers. And so the interaction model was to have the connects, there are 2 connects, recognize human gestures, some of them, and then to map them onto the marionette gestures. And so what the artists wanted was gestures like, wanted little Bill to sort of look down and look shy, or for him to jump up and do this, but in response to what the people did. And we couldn't, it wouldn't work if it was predictable. And if you look at a lot of the things in museums that are gesture interaction, one way to help the person learn what to do is to have the system mimic the person. And we didn't do that, no mimicry. It was stochastic. And because of that, people would engage and they'd try and figure out, I wonder why he did that. Or what's he thinking? How come he's not paying attention to me? And it engaged them mentally in a way that mimicking doesn't. So we used Microsoft Connect. We used the Connect SDK library. We used an Arduino on board to raise and lower the strings to move the marionette around. And the marionette was constructed from 3D printed components. We also put a motor behind the eyes to make him blink, because the blinking was really effective. That made them think he was alive. So now comes the design. How do you design the marionette gestures? Which gestures do you do? How do you match that to the strings? Which is an MP complete problem, because the strings are not, it's a plastic material. And so after it moved a lot, you didn't know where it was. You couldn't calculate that. And so we just decided, we decided that we couldn't do that. You can't, it's an MP complete, MP hard problem. So we had a gesture that was called sort of a sigh, where he would sort of be lifted up and dropped back down, and we put him back to 0, and then he would start again. And so we solved the problem by not solving the problem, by avoiding it. So we did a whole bunch of methods. We did body storming, role-playing, personas, image boards. We did a think aloud gesture elicitation study, and we came up with a few design principles. Don't mimic. The responses from the marionette are intended to evoke a response from the person, and continuous movement so that it felt like the marionette was alive. And it was interesting. We did a lot of studies on this, that depending on the person's perspective, again, those mental models are so important. When we had participants who were not tech savvy, so they were just normal people, doctors or children or someone who doesn't study HCI or computer science, they immediately ascribed intelligence to the marionette. They described the experience as interacting with this thing that was clearly a machine, but they personified it immediately. That uncanny valley had been passed easily for them. And for the people who were tech savvy, they came in and they interacted very differently. They sort of, how far does the camera go? If I go over here, does it see me? If I bend down, what happens? And they were like testing it to see what does it do. And that was fascinating, because their stance, their mental model, and their interaction repertoire was completely different. And so here we are designing these public displays, thinking that there's a user, and we're going to figure out what that user is thinking, what their mental model is, and we're going to design for that. But actually you have to design for multiple mental models. Okay, just about done. I just want to identify a couple of the design challenges and the research challenges, and then have a conversation with you. So the design challenges, embodied generally, is how do we understand embodied interactions as user input? How do we convert from the way we are in the world and use our bodies, which is not to put input into anything, it's to communicate. And when you think about a computer system, it's not always communication. The marionette was, but the command system wasn't communication. I wasn't communicating per se, I was commanding. For the Siftio cubes, I'm not communicating with the system. I'm moving things around to solve problems. So how do we make that transition as interaction designers to use our bodies for something that is about input? Secondly, how do we provide visual feedback? That's really tricky. How do we know it interpreted our actions correctly? And how do we know as users that it's carrying out my intention, not just got the right gesture? And then the sensing technology is really a really difficult sort of engineering problem, but also a design problem. How do we make sure that what the person thinks to do, for example, stacking one Siftio cube on top of the other, everybody wanted to do that used our system. But the Siftio cubes don't sense stacking. They only sense shaking and neighboring. And so how do we communicate that, and how do we design for that? And then here's the research challenges, and I'll leave it here after I describe this slide. We are, in fact, designing gestures. I don't know, other than sign language, I don't think we've ever had a field that designs gestures. And what I mean by that is, if the system is going to be able to sense that this body movement means something, then we've designed a gesture. And now we're telling humans they have to perform gestures as designed in order to interact with the system. So that's different. How do you design gestures? You have to design them before you can recognize them. I think it's a real challenge, this multidisciplinary research. I think it's a challenge because you can't really do it well unless you bring this really unusual group of people together, and that doesn't happen very often. The third one comes back to that research that we did that showed that tangible increased creative cognition. Well, in a certain context of use it did. In another one, it inhibited creativity. And so as we're thinking about embodied interaction, it's not the answer to everything. And tangible shouldn't replace touch for everything. It's appropriate for certain contexts of use. And what are those? How do you find those contexts of use and take advantage of embodied interaction? Limited scope of representation. So what this means is that as soon as we put something in strong, specific devices where the physical entity itself is meaningful, we've limited the scope of the representation. We can't change the size of that hockey puck that is the physical object to match the use. So we're constrained by the physicality, where physicality is one of the benefits, but it also constrains us. So when we're thinking about things like parametric design in a CAD system, how do tangibles assist with parametric design if the change in parameters space can't change the size of the physical tangible object you're interacting with? And then cognitive and physical fatigue. There's a lot of things about interacting in an embodied way that are completely different to this keyboard and mouse. And that is physical fatigue, which is really easy to observe, but cognitive fatigue. You don't want things to be so hard to figure out mentally that you've replaced cognitive disfluency with cognitive difficulty. Thank you for listening, and questions?
Thank you for this talk. I found it extremely stimulating. When I use gestures, I'm trying to indicate to somebody I'm communicating with some little grace notes or something about what I'm talking about. And that's not a command. And yet, I see what you're doing as almost turning them into commands. Maybe that's not at all natural. And when I do commands in my current world, the physical world, leave aside the computer world, I'm moving things around or bashing them or something like that. And maybe it isn't natural for gestures to be commands, but we do have examples like conductors or supervisors of job sites and traffic cops and so on. But it doesn't seem to be natural, which maybe leaves it open field. You can create your own grammar because there isn't a natural grammar there. But still, it seems like a problem that we aren't naturally thinking of gestures as commands, and you're using them as commands. Maybe there is a way to use them in a computer system where it's not a command, but I don't know of it right now.
So in psychology, they've studied gestures a lot. And McNeil came in 1982, he came up with these categories of gestures. And some of those gestures are commands, pointing, moving to give a sense of what's happening physically. Like when I say shake the cubes, I do this. And so it has meaning, visual meaning to what's being talked about. And you can think of those as being translated into commands. The problem is we don't have any standards. We all make our own gestures. We don't worry about whether you're going to figure out what mine means, because I'm not doing it for that. I'm doing it for some other purpose inside my head. We found that people gesture even when there's no one looking. So if you ever see someone on a cell phone walking down the street and they're like gesticulating all over the place, clearly not for the person they're talking to, right? Because they can't see them. So gestures have many, many uses in our lives, and in our thinking, and in our communication, and in our commands. If I were to give you directions to go somewhere, I'd probably point and say, you go down there, you turn left. So some are commands. So it's not fair to say that we're not commanding. Sometimes we are. That's why I think context of use is everything. If you're going to build a gesture interaction system, you want to think how to use gestures in a way that's beneficial rather than just because we can. We have this technology, we have these connects, we have these leap motion controllers, we can. But we shouldn't do it just because we can. We should actually do it because there's some cognitive gain. And that's the challenge.
Very interesting talk. Lots of questions. I'll try and limit them right now. The first thing that comes to mind when speaking about gestures is the input bandwidth that you're talking about from one of these devices. And it looks to me like the bandwidth is much like a phone that you don't know how to use. Have you thought about the types, or at least have you thought about the types of interaction that would be useful for this thing? And like the things you've built, have you figured out stuff that you shouldn't do? Because as I say, the question of bandwidth and of the interaction space seem to limit what you can do with these things.
So I think we're beginning to see whether I think it's a good idea or not, or you think it's a good idea. We're seeing more and more of these in public spaces and in museums. And when you talk about bandwidth, when you walk up to something in a public space, you're not going to be working at that for hours. So it's not like I'm going to get tired because I do this 8 hours a day. Nobody's going to be doing this 8 hours a day. So don't worry about that kind of fatigue. Also in museums, these are exploring these gesture-based interaction systems like the willful marionette are causing us to explore our bodies in really interesting ways. So, for example, one of the people who was interacting with Little Bill the marionette, when we interviewed her afterwards, she said it made her so aware of her body that something was sensing it and interpreting it, that it made her afraid to move in the beginning. And so they're provoking us. These art installations are helping us think about our bodies in ways we haven't thought about them before. But now let's think about, other than art and public displays, are there other places where this could be really helpful? We already have sign language. It's only a matter of time before a deaf person can sign to the computer and it'll type for them, or it'll communicate, it'll capture what they've been saying. There are places where gesture is essential. If you're doing surgery, you don't want to touch a screen. You either want to talk or you want to gesture. So there are places where the context of use makes gesture interaction almost an imperative, because everything else is less good in some way. So I think we're finding this because the technology has become available and inexpensive, but what my work is about is let's be aware of the cognitive issues before we just go and build it because we can.
Just a short follow-up. Have you considered using essentially sign language and very small gestures in front of a camera instead of a larger Connect-style gesture?
Yeah, so the leap motion controller is a very small little device that can be mounted where your webcam is, and it specializes in sensing the movement of the hand, and that's not the whole body, just the hand.
Thank you. Have you had, could you comment on any work you've done with profoundly disabled individuals that would have the thought of the action, but the inability to have the action?
Not in my own work, but there's a lot of work in this space in a couple ways. One is they've found that children on the autism spectrum disorder that's sort of on an extreme end are more likely to collaborate with each other if they're not looking at each other. And so gesture interaction on large wall displays allows people with this kind of brain structure to engage in ways that they wouldn't otherwise do. So there's been some studies with that. In terms of the profoundly disabled, like locked-in syndrome, that's mostly going to, if they can move their eyes, tracking eye gaze, and if they can't even do that, then it's usually implanting electrodes or putting EEGs on to interact that way, rather than moving the whole body. For people doing physical therapy for other kind of disabilities, gesture interaction is a way to give feedback on whether they're doing the action correctly. And so the Connect will sense what they've done and will tell them, you know, raise your hand higher or lower or whatever. So gesture interaction in that sense is like a coach. So I haven't personally, but certainly it is a really wide open field for thinking about how embodied interaction of any kind can facilitate that. Hi.
Hi. Just a little bit of a follow-up. There was it seemed like 2 questions regarding sign language. Is there anything that you have come across or could learn from, I guess, the learning curve of sign language, or even, you mentioned 2 groups, the HCI group and I guess the non-HCI group starting off. What about maybe people who are fluent with sign language? Would they already have some kind of standard built into gesture? Has that ever been studied? And is there any sort of naturalized gestures between different types of sign language that could start to form, I guess, some kind of starting point? And again, also thinking about fatigue and the range of vocabulary with sign language, is there anything that you can learn from that? Or anyway, yeah, thanks.
Yeah, I think we can learn a lot by looking at sign language when we start to think about gesture interaction, because that is body movement intended to communicate something very specific. It's not quite a command, but at least it's something specific. In terms of the learning curve for sign language, I don't know. I imagine technology could help with that too, because you could be trained, not by looking at something, a piece of paper that tells you how to do it, but you could watch yourself do it. Sort of like the Rosetta Stone for learning language, where it shows you when you pronounce a word in another language, it shows you where you went wrong by showing the sound waves. But in terms of that creating some sort of a standard, or can people communicate that way from with different sign languages? If you know American Sign Language and someone else knows Australian Sign Language, they have trouble communicating. Just like if I were speaking to someone who's speaking German. So they are different gestures to mean the same things emerge out of these languages. So I'm not sure what we can learn from that, except it's a language.
Great, thanks for the talk. I just had a question about embodiment, and there's been a couple of questions about like the size of the gesture space, but is there a distinction, like from a cognitive science point of view, between like micro gestures that are maybe just like twiddling your thumbs while you're typing, or even like athletes who chew gum, or I've even seen stories that could help with studying or focus, and I know there's little fidget spinners that have been deployed recently. So which are all these like sort of micro repetitive gestures we do with small muscles versus the big full body motion? Is there a difference in terms of like what the positive benefits of those 2 types of gestures might be?
You know, the only literature I know, and that doesn't mean it's not out there, is the work that psychologists have done in trying to categorize gestures and why or what those gestures mean to us cognitively. But in terms of something more broadly, I don't know. Is there anyone else here who knows whether that's been studied by psychologists? I just don't know. I think with all this advent of being able to sense gestures, I think that's really going to open up this part of psychology. Like, we're not going to do this by ourselves because we're HCI people. It's actually going to open up in psychology, what is gesture about? We've been able to study it so far in the context of human-to-human communication, but it's got to be bigger than that.
Justin, the thought of large gesture and small gesture. My first thought is, that takes a long time. That's really fast.
Yeah.
It's a Fitts law problem. So anyhow.
I thought they took the same amount of time. Maybe less energy.
You were talking about the hockey pucks being one size, and that might be a problem. Why not make different size hockey pucks? Doesn't seem that difficult.
I mean, once it's made, it can't change.
Right.
Where digitally, you can reconfigure the size of objects on the screen easily, but you can't reconfigure the size of physical objects easily.
Right. So I'm just thinking Lego bricks come in multiple sizes. Why not hockey pucks?
But you can't change each one.
Can't change each one.
So, right, you might want to have the tangible objects that are sensed. So one way that people have done this, which is pretty cool, is, are you familiar with the Osmo tangible interaction system? So basically it puts this little camera, this little mirror over the camera on your tablet or your laptop, which means that the input for the application is whatever's in front of the tablet or the screen. And then you can put objects of any size. You can draw your tangible device. You can put your hand there. And the interaction with the system then is just based on whatever physical thing is in front of it. So now, putting technology in the physical object isn't needed. It can be sensed from this simple camera device, and that can be used as a basis for input into your application. I think that opens up that problem of we can't change the size, but we can change it if it's just a camera that's looking at it instead of the thing itself has sensor technology that makes it spatially aware.
Another problem you mentioned was that people tried to stack the, I don't know what the word is, Siftio?
Siftio cubes. Those are those cubes with a little display on it.
Don't know how to spell that, but if you just put a handle on the top, then they couldn't be stacked.
Oh, it would be very easy to sense stacking, but they didn't do it. The people who delivered
It, the people intuitively would know not to stack if there was a lump on it.
But stacking is meaningful. The point was, it was meaningful, but they hadn't accommodated it. Not that people shouldn't stack things that can't be stacked. I'm sure you could figure out a way to do it so that if they stacked it, it would fall off or something.
Right.
But the point was, stacking was meaningful for the person who was working with the cubes.
So it's a false affordance or something.
It's a false affordance. Very good. Yes. Well, thank you very much.
Yeah, just a couple quick announcements. We'll be meeting again in 2 weeks at the DGP lab at University of Toronto. Fanny Chevalier and Saeed Ishtiaq Ahmed will be presenting. There's also 2 events coming up here in this space. February 22nd is the Future of Hardware, where 3 product designers and medical innovation companies will be discussing tools, their use, and the future of making things. And on February 28th is How AR is Shaping Our Reality with Dr. Helen Papangiannis. So both should be interesting events for this community. All right, thanks everyone. See you in a couple weeks.